All right, let's go ahead and go over some of the problems from test one. All right, I'm going to be just picking a problem off one of the versions, and then the other version is similar, and you could figure it out, I think, based on that. Both questions 1 and 2 were trying to figure out the limit by using a table of values. On number 1, the x values in the table were already given to you. In table 2, you had to come up with what might be good to plug in. On both of them, though, the major mistake was not evaluating the expression correctly. Okay, so I wanted to look at question number 2, where you had to determine what to plug in. So what you had to decide was, the values for when you're coming from the right and the values for when you're coming from the left, getting closer and closer to 3. So it might be good to pick something like 3.001, 3.01, and then maybe on the other side do something like 2.999, which is really close to 3, but maybe start with something like 2.99. You didn't have to pick those exact things, but those are good ones to do. All right, and so let's just do one of them. So what happens is, what you've got to try to evaluate is this. The 3.001 minus 2, you take the square root of that, take away 1, and divide all of that by 3.001 minus 3. All right, so if you're going to try to enter that in one step, let me come down here and show you what it would have to look like. You would have this little square root. It would give you a left parenthesis, and you could put in the 3.001 minus 2, close that parenthesis, subtract 1, but then that whole thing would have had to be in parentheses because this is a grouping symbol. So all of that has to be worked out. And then once you get that, you divide it by what this turns out to be. Okay. So it's kind of a pain to enter it in one step. So it might have been good to just figure out the denominator. You can see that would be 0.001. And then what I normally do is I enter this in my calculator, type it in like that. Okay, so enter this part in the calculator and hit enter. Then divide by the 0.001 after you're done. Okay, so when you work that out, that should have turned out to be, let me go back to what it turned out to be. So that turned out to be, to 6 decimal places, 0.499875. Right, and that was right here, right? And so then you did that for these other values, and what you should have observed is that we could estimate that the limit as x approaches 3 would be 0.5, okay? Because you're going to get, like, on this side, let me erase that, you're going to get over here, this one turns out to be like 0.500125, where that one turned out to be 0.499875. So the limit as x approaches 3 appears to be 0.5. Now that is actually a problem that you could calculate by analytic methods. You could rationalize the numerator and then figure it out that way. Okay, but you weren't asked to do that. You were asked just to use the table. So pretty much just be more careful when you're trying to type that into your calculator. All right. All right, now the graph, I think once you see it, you can see what happened there. Let's go ahead and look at these problems where you had to just find the limit analytically. Let's go ahead and do the one. On one version, it was a cosecant. On another version, it was secant. And you were asked to do it analytically. So basically, you had to think about taking the x you had and just plugging it in, right? And trying to find what was 4 cosecant of 3 pi over 2. So we have to think about that. So we have to be over here at 3 pi over 2, because this is pi over 2. Okay, 1 pi over 2, this is 2 pi over 2, this is 3 pi over 2, and then this is 4 pi over 2, which is back at 2 pi. So here's where we'd be. And remember, on the unit circle, the coordinates of that point actually give you the sine and the cosine. So we know this would be the cosine of 3 pi over 2, and this coordinate would be the sine of 3 pi over 2. Okay? So then what we do is we know this would be the limit, but we need to evaluate cosecant of 3 pi over 2. So it helps to remember that that's 1 over the sine of 3 pi over 2. And you know that sine is -1 at 3 pi over 2. So that's 4 times -1, which would be -4. So the answer to number 7 would have been -4. All right. Now, number 8 was not a difficult problem, but it's related to some that we're doing when you were asked all about vertical asymptotes and that kind of thing. Number 8 was kind of the key type of question to understand. So if you tried to plug in 7 as is, you'd get 0 on top and 0 on the bottom. Okay. So what you do is you use algebraic techniques to try to see if you can take care of that trouble spot that we have at 7. So you factor the numerator, you factor the denominator, and notice it would be a 7 and a 3, need to be -7 and +3. Once you get it in factored form, you notice that you've got x minus 7 as a factor common to the top and bottom. So the limit of the original expression would equal the limit of this expression. At 7, we would just have a little hole. So it would be fine to cancel that out and do the limit at, so that equals the limit as x approaches 7 of this expression, which no longer has the trouble spot. So we plug in a 7, top and bottom, and we get 14 over 10, which is a fraction that we can simplify by dividing by 2. So the answer to that would be 7/5. The other version was very similar, just had slightly different factoring. Okay. Now, number 10 on one version and 9 on the other involved this 1 minus cosine x business. Now, that was one of those 3 special things that you needed to remember, like the limit of sine x over x as x approached 0 was 1. And then this was the other special one in there. So this is the same as that. And we could pull the constant out and do the limit of this 1 minus cosine x over x. Okay, all of that. And that was one of those special theorems, and the limit as x approaches 0 of that is actually 0, and 3 times 0 would be 0. So your answer on number 10 on this version and the 9 on the other version should have been a 0. Now, when you're not sure, when you know it's a special, like you should have been able to recognize that this was one of those special theorems you needed to know, but you might not have remembered whether it's a 0 or a 1. Don't forget, you could test it by coming in and maybe putting like a 0.001, something really close to 0, to see what it seems to be approaching. Okay. All right. Now, that one isn't that important in the bigger scheme of things, but it was one of the harder ones on the test. Now, number 8 on one version and 10 on the other involve these rational functions that we sometimes get. So here the algebra was a bit of a challenge. So we would multiply by the least common denominator, which is 8 times x plus 8. We're multiplying the entire numerator, so it got distributed to both terms, and we have to multiply the entire denominator. Okay, so we're multiplying the top and the bottom of the fraction by 8 times x plus 8. All right, we do that because it winds up simplifying the complex fraction to where you have this 8x, x plus 8 in the denominator, and then in the numerator, see how you have 8, then the minus, and then here the 8 cancels, and we have this x plus 8. Okay, so when we distribute the negative right there, that makes the numerator 8 minus 8x minus 8 over that 8 times x plus 8. Okay, so the 8 and the negative 8 cancel. We also are going to be able to knock out the x from here, okay, leaving us a -1 on top and an 8 times x plus 8 on the bottom. Now, we haven't done the limit yet, so let's keep that in there. We still need to do the limit, but we were able to get rid of the trouble spot, which was having that x down here in the denominator, okay? So what we're able to do now is just direct substitution. So that's kind of what all the techniques that you learn are all about. It's trying to see if there's a way to adjust the problem so that you can just use direct substitution. You just might have to do a little algebra first. So now we can plug in the 0. We get -1/64 for our answer. Okay. And I'm trying to select problems from both versions of the quiz so that I'm not always just working out one person's one version. Okay. All right. Now, number 11 was kind of like the other factoring problem. It's just it was hard to remember how to factor the cube. So when you factor a cube, it's a formula that you can remember. You know it has to be an a squared and a b squared. You just needed to remember it was an ab and then get the signs right. By the way, you could also divide, like, let me do it up here. You could take the x plus 5 and divide it into the x to the third plus 125, but you'd need to put in a couple of those placeholders when you did your long division. Or if you wanted to, you could use synthetic division, put in -5 in the box, and then use these, if you remember that, okay? But that numerator would factor, okay, into x plus 5, and then you'd have x squared minus 5x plus 25. And so now you're able to knock out the x plus 5, which was the trouble spot, and the limit of the original expression would equal the limit of just x squared minus 5x plus 25. Okay, so you plug in the -5 at this point, and you wind up getting 25 plus 25 plus 25, which turns out to be 75. So this would be 25 plus 25 plus that 25. Okay, so just trying to remember how to factor the cube is what caused the most problem, I think, there. All right, but you notice how what we were trying to do is get rid of the trouble spot. See that x plus 5 that we canceled out? That was the whole point of the questions that came up later about whether you had a hole or a vertical asymptote. Okay, this at -5, we would have had a hole in the graph, which is a removable problem. It's not a big deal because we could cancel out that common factor, and then the limit of the original expression we could find by using direct substitution. If you were unable to cancel that out, you would have had a vertical asymptote there. Okay, so it would have been a completely different level of difficulty. Okay. All right, number 12 had some algebra that you needed to remember how to do. On one version, I put the radical in the denominator. On the other version, I put it in the numerator. But when you see radicals like that, if you have that 0/0 situation, when you test, when you plug in the 4, then when you see the radical, you should think, hey, why don't I multiply by the conjugate, which is everything exactly the same, just with a plus here, since the original problem had a minus, okay? You don't square the top and bottom. The expressions wouldn't be equivalent if you squared the top and bottom. You have to multiply by the same thing on the top and bottom. And the reason you're picking the conjugate here is because of what it does when you multiply that out, when you FOIL that out. When you do square root of x times square root of x, you get x. Square root of x times 2 would be plus 2 square root of x. Then you come back and you do these two and get -2 square root of x, and then -2 times 2 would be 4, so you'd have -4. -2 times +2 would be -4. So you see how the inside terms cancel and you wind up not having any radicals in the denominator, okay? Now on top, I'm going to leave it with that x minus 4 so that you can see what happens, because we had an issue when we plugged in 4 originally. But now what we have really is x minus 4 times this square root of x plus 2 on top, and we just have x minus 4 on the bottom. And it turns out then that that x minus 4 could cancel out, and we could just do the limit of the square root of x plus 2 as x approaches 4. And we can now do it by direct substitution. So we plug in 4 for x, we get 2 plus 2, or 4 for our limit when we're finished. Okay. All right, so you had to do the rationalizing concept because it had a radical in it. So that was one of the important skills, was that idea of rationalizing. Another important algebra skill was trying to get rid of these denominators. When you have a rational, when you have like a complex fraction, you have these rational expressions. And then the other skill, that algebraic skill you use a lot, is the idea of factoring, like we did on number 8 and like we did on number 11. Okay. All right, now 13, it was just an E, so you wound up not being as sure of yourself there. But using direct substitution, we could plug in the 3, and the exact value of your answer would be e to the 5th. And many of you plugged that into the calculator to get a decimal. And I didn't really count off for that, but that's not an exact answer. Like when you plug that in, you would have gotten this to be about 148.4, but that's not an exact answer. So this would have been better to just leave it as an exact answer. Okay. All right. And then let's see, one test had e to the x plus 1 instead of e to the x plus 2. Okay. All right, so let me see. I'm going to go ahead and stop on this and do another video on the next session.